last stuff we're going to do this semester. We'll probably look at just a few other topics after we're done with this. So what we're going to look at is just how you look at numbers and tell if something is an exponential or linear relationship or neither. And it's actually pretty easy to see. I think you'll do this just fine. So let me just take this example, kind of zoom on this and show you how this goes. So the way a linear relationship works is like this. Let me make sure I get this. Yeah, I'm recording. Make sure. All right. So the idea is, notice that as you go up by 1, y is going up by 5. Okay. And here's another thing right there. The 3 goes up 1, so the 20 goes up by 5. All right. So basically, you would have something kind of like this. If you have 0, 5, I kind of left, there's a few missing numbers on there, but 2 would be 15. I didn't put the 2 on there. 3 would be 20. 4 would be 25. So what do you predict 5 would be? 30, right? You just keep going up by 5. So what we say is this is a common difference. So the idea on linear is if you go up the same amount on x, then you're going to go up some common amount on y. Okay, so it just means you're going to keep going up. We call that a common difference. So we would say the common difference would be, and it doesn't matter what order you do this in, you could do 5 minus 10, or you could do 10 minus 5. You get a common difference of 5. That's how you know something's linear. So as x goes up, y goes up the same thing over and over again, up whatever. Okay, exponential is totally different. So notice this one does not go up the same. On this one, that's going up 2, and then that's going up 6. So right there, you know it's not linear. So what happens on exponential is you have what we call a common ratio. So, and it doesn't matter which order you divide these in. You could go 1 over 3, or you could go 3 over 1. That's a ratio. So what would have to happen is that ratio would have to be the same over and over again. So if we do it this way, that's 3/9. What does 3/9 reduce to? A third, right? Okay. Or how about 9 over 3? What's 9 over 3? 3. Okay. So the idea is the ratio is always the same. Look at the next one. Okay. You can just do it one way. 27 over 9, isn't that still 3? Yeah. How about 81 over 27? Is that still 3? Okay, that's what exponential functions look like, is the ratios are always the same. And again, x has to be going up the same amount. Okay, so you want kind of look and pay attention to missing terms on this. Now, what would happen on this one is you notice the x's are going up 1, but if you did like a difference, if you do -1 minus 0, then 0 minus -1, then 3 minus 0, and 8 minus 3, you're always getting something different, aren't you? Okay, so that right there, the fact that we're getting different numbers for differences tells us that it's not linear. We can forget about that one being linear, okay, like that, all right? So now what we got to do is we just got to look at the ratio. Well, I'm going to start down here. We'd have 8/3 if we did that ratio. Then we'd have 3 over 0, which is undefined. Then you would have 0 over -1. None of those are the same, are they? So that means it's not exponential. Does that make sense to you? Okay, so what's linear? How do you tell if something's linear? Tell me. What do you look for? Common difference, right. What's exponential? What do you look for? Common ratio. Exactly. Okay, so it's real simple to spot. Okay, so let's do kind of a round of these together. Okay, now you notice on this first table, all of these things right here just keep, the x's are going up 1. And that's what you want, is for those things to keep going up. And if they keep going up by 2, that's still okay. So let's look at the difference on this, okay? And just kind of look at this. We would have 7 minus 4, 4 minus 1, 1 minus -2, 2 minus -5, -5 minus -8. All right, are those all the same number? 7 minus 4 is 3. 4 minus 1 is 3. And even this one, 1 minus minus 2 is still 3, isn't it? So what you have is you have a common difference of 3. All right, so is this linear or is it exponential or neither? Linear, thank you. Okay, so that's linear. We don't have to worry about the ratio. Okay, I'm going to go ahead and do the ratio though. All right, so that one has a common difference. If you did the ratios, it would go like this. That would be 7 over 4. That would be 4 over 1. That's good enough. Those are different. 7 over 4 is not the same as 4 over 1. So you're going to have there's none on a common ratio. So that's linear. Okay? So you want to get to where you can spot these things fairly easily then. Okay? All right. Next one. Okay? Let's look at the differences. And you don't have to do all of them. If you see they're different, if the differences are different, then it's not linear. Okay? So it doesn't matter where we start. Let's start there. 3 minus 1 is 2. And then 9 minus 3 is 6. Okay, so what does that tell you about the common difference? Is there one? No, there's not one. Okay, so that means that this thing is not going to be linear. Okay, it's not linear. Okay, now what we're going to try now is we're going to try the ratio. Okay, and let's see, they all got to be the same, so let's try that. Again, it doesn't matter what order. I just take the biggest number divided by the smallest. So 81 divided by 27 is 3. If you don't know that, do it on your calculator. Now let's see if all the rest of them are the same. 27 over 9, that's 3. Okay, next one. 9 over 3 is 3. 3 over 1 is also 3. And then even this one right here, if you do 1 divided by 1/3, that's also 3 because when you divide fractions, you multiply by the reciprocal. Okay, so the common ratio is 3. So which is it, linear or exponential? Exponential, good. Okay, so that's how you tell. Okay, so this is just kind of getting you started on what the idea of an exponential function is. Okay, everybody with me? Okay, common difference, linear, common ratio, exponential. Otherwise, it's neither. Okay, so let's go to the next one. Let's see if we got a common difference. So 15 minus 8 is 7. 8 minus 3 is 5. So is that linear, yes or no? No, it's not linear. There's no common difference. So we know that it's not linear. Okay, it's got to be the same everywhere. Now let's do a ratio. Okay, let's do 15 over 8, which you could use a calculator if you wanted to. 8 over 3. 3 over 0 is undefined. Are those the same number or are they different? They're different. So is it exponential, yes or no? No. Okay, so there's no ratio on that. So that means that is neither. Okay, so the two things that you always want to check on this are, number one, always check that your x's are going up by the same amount. All of these for simplicity are just going up by 1. The x's go up by 1. So either make sure the differences are the same or the ratios are the same. That's how you differentiate between exponential and linear. Everybody okay, you think? Okay. Well, let's do one round of problems and let's see if you're okay, all right? So all you want to do is just check for a common difference or a common ratio. Okay, you can kind of write a little bit of scratch work on there if you want to. You can maybe do these in your head. I think I can do these in my head. Okay, but write down whatever you need to as a student on this. Look, check for the ratio or difference. That. Okay, let me put up here what my answers were, and I think we were doing okay. I maybe didn't catch that something on that last one, but this first one, you can see the differences they're all different. 32 minus 8, all those differences are not the same. The ratios are not the same, so I just did 32 over 18, 18 over 8, 8 over 2. If you have to use your calculator and turn those to decimals, you could. but they're all different. So that one is neither linear or exponential, okay? The next one does not have a common difference. It's easy to see that in your head. 100 minus 20 is 80. 500 minus 100 is 400. You just look at two things and you can tell the difference is not the same. But the ratios are the same. So you just always get 5. Or if you did it backwards, if you did like 20 over 100, you would get 1/5. So their common ratio is always just going to be something or the reciprocal. Okay, that's what happens on that. So that's exponential. And then the last one is linear. Again, I left out the 2, so you really would have, inside there, you would have a 215, but they all go up by 5, so they do have a common difference. Okay, how do we feel about that? Do we understand? Okay, all right. Okay, very good. Okay, so as we kind of proceed through this, we're going to look at what exponential functions look like. So the last part of the semester, we talk about exponential and logarithmic functions. So we're going to look at this type of form right here. So exponential functions are always going to look like this. You'll have some number, then you'll have some other number to the x power. Okay, that's what we're going to look at for the structure, is something that looks like that. So we're just going to learn how to identify these, and then we're going to talk about what we mean by a growth and a decay function, okay, which are pretty easy to see. So this function right here has that same structure, ab to the x. Notice on this I've got f of x equals 3 times 5 to the x. So that a is 3 and that b is 5, like that. Okay, here's how you tell if something grows. Let me first of all do this on your calculator. If you have your calculator with you, I hope you do, then I would recommend strongly that you put this in your calculator so that you can understand what I mean by growth and decay, all right? So go to y equals and just put this in like this. Just put in 3 times and then put in 5 raised to the x power like that. Put that in a standard window. You can just go zoom 6, and this graph goes like this. So if you look at this graph, it's getting bigger from left to right. You can tell it's growing. So you can also kind of look at it this way. If you look at your table of values, the y values are getting bigger, aren't they? And this is an exponential function. I want you to check this out. What's 15 divided by 3? That's 5, right? What's 75 divided by 15? It's still 5. So you have that common ratio. So this is an exponential growth curve because the y values are getting bigger. The graph is getting bigger. The way you tell that is if this number right here that you're raising to the x power, if that's bigger than 1, then it's an exponential growth function. You don't have to do that by graphing. That just means you're growing automatically. The graph's going like this. Exponential growth curves look like that. Okay? The next one, let's put this in our calculator. Let me show you what this looks like. So if I go to y equals, I'm going to clear what I had on the last problem. I'm going to put in this function, exponential function, so 2 times, and then you have to put this at 1/3 in parentheses, like that, and then raised to the x power like that. All right, so once you get that put in, and if you do your graph, what's the difference on that? What's happening to the function? Is it going down or is it going up? It's going down. That means decay. Decay means everything's going down. If you looked at your table of values on this, you're still going to see that common ratio on here. It's kind of hard to see, but notice 6 over 2 is 3, 18 over 6 is 3, but what's happening is the y values are getting smaller. So this is what you would call an exponential decay function, and the way you tell it's a decay is that number that's being raised to the x power is between 0 and 1. So that's how you tell. Okay? So let me just, before I go to the next page, let me just check you on something here. What if you had 2 times 10 to the x? Just by looking, is that growth or decay? Growth. How do you know? What number tells you it's growth? this one. Since that's bigger than 1, that's why it's a growth function. Okay? All right, here's another example. 3 times a half to the second. Growth or decay? Decay. How do you know? The half is between 0 and 1. That's how you know it's a decay function. Okay? Everybody got that? Let's see what's happening is you're taking a big number to a power. Big number to a power makes things get bigger. Like 10 to the first, 10 to the second, 10 to the third is going to get bigger and bigger and bigger. But if you take a fraction to a power, they get smaller and smaller and smaller. That's what happens. Okay? All right. So here's kind of how this looks. This is how graphs basically look like this. So this first graph I have on the next page is f of x. Technically, it's 1 times 2 to the x. Okay? And one thing I want you to see kind of on this is how these points go. So what you're really doing is you're just plugging in these x values. Like 2 to the first, for instance, is 2. So you get this point when x is 1, 2 to the first is 2. This next point right here, you're doing 2 to the second is 4. And then this point right here, you're doing 2 to the third is 8. So what's happening to these values is it's growing because that 2 is bigger than 1. That's what causes that to happen. Okay? This one over here is the function. Technically, this would be 1 times 1/2 to the x power. And again, what's happening with these points is the y values are getting smaller on that. Okay? It's because that thing right there is between 0 and 1. That's how you tell it's decaying. Okay, are we okay? Okay, we're just trying to look at what makes something growth and then what makes something decay. All right, so here's what we're going to try to do to begin to put this together. Okay, so if it's an exponential function should look like this. You should have a number times another number to the x power. Now, you can have a few little differences in there. The basic idea is you want to have something, some number times another number, and then you want to have variables in that exponent. Okay, this one right here has that same structure. A is 1/4, B is 7, so that is an exponential function. Okay, is it growth or decay? Why is it growth? 7 is bigger than 1, exactly. So this is a growth function. And the reason it's a growth function is that 7 is bigger than 1. That's how you tell. Okay? All right? Okay, next one. You have a number times a number to a power. Okay? So that is definitely an exponential function. Is this one going to be growth or decay? How do you know? There you go. Now, it's really the reason is that 1/2 is less than 1, but it's bigger than 0. It's got to be in the middle of 0 and 1. That's how you know it's decaying. Okay? Okay, the next one. Does this look like an exponential function? Does this look like the same as A and B, or does it look like something totally different? That's different. Do you guys know what this function is? Linear. That's linear. Okay, it's y equals mx plus b. So that is not an exponential function, so we're not going to worry about whether it grows or decays. That's a linear function. Okay? Okay? How about the next one? Does that look like an exponential function, or does it look like something else you've learned? What? It's not exponential. Here's why it's not exponential. Because you have a number 4, but then you don't have a number, and then that's got to be an x power. See, is not an x. You always have to have, like A and B, a number times a number to the x power. This one is quadratic because it has a second power in it. So that one, if you graphed it, it would have a parabola like we've learned. Okay, so that's no. Okay, A and B is what they got to look like. Okay, with some slight little twists to it. Okay, all right, so the next one, again, it has a number, and then it has another number raised to a variable power. This is a yes. Even though it has x minus 2, that's still okay, because this would just be a transformation of this, okay? So that one's yes. Now, is this decay or growth? Look at the 2.5. That's what tells you. Which is it? That's growth. How come? 2.5 is bigger than 1, right? Okay, so that one is a growth function. Again, the 2 is bigger than 1. That's how you know, okay? All right, so essentially what you look for is that your exponent has to have x in it. You have to have a number, and technically this problem is saying -1 times 0.2 to the 3x. That is an exponential function. It's okay that it's 3x. It's okay that it's 2x or x plus 2 or whatever. That's fine. As long as that exponent has x in it, then it's exponential. Okay, so now what you do is look at 0.2. Does the 0.2 make it growth or exponential? Or no, growth or decay? I'm sorry. Decay. Good. Okay. So that's the idea. The idea with decay is basically going to be that the 0.2 is in the middle of 1 and 0. So that's how you do that. Okay? So notice all these problems that we said yes on. These problems right here all have the same structure. What do you have? You have a number, another number to a power, and that power has a variable x in it. That's how you tell. Okay, are we good with that? Okay, and the number that tells us it's growth or decay is the number that's being raised to a power. Okay, that's how we see that. Okay, next thing I want to go ahead and go through is evaluating. So evaluating you won't have much trouble with, I don't think. You'll be able to use your calculator some, but most of the time you're not going to need to do this. So if we have an exponential function, that is an exponential function. It's an exponential growth function because of that 2. We just want to find f of 2. So what do I typically do? I replace the x with 2, and I work it out. So you're going to have 4 times 2 to the second, and then we need to work out that arithmetic. And don't do all these on your calculator because you want to follow order of operations. You do exponents before you multiply. So 2 to the second is 4. That would be 16. Okay, so that would be your answer to that problem right there. That's what f of 2 is. That just means you have the point on the graph 216. Okay, next one, same idea. This is an exponential function. Just plug in the -1. So when you do f of -1, we'll have 3 raised to the 2 times -1 minus 3 power. Okay, work out the arithmetic. That is going to be -2 minus 3. So that's 3 to the -5th power. All right. Now, we've done this before a little bit. If you have a negative exponent, do you guys remember how you make negative exponents positive? It goes to the denominator, right? Okay, so you would write this as 1 over 3 to the 5th. Then you want to go ahead and take your calculator. I'm pretty sure 3 to the 5th is 243. I think anyway, let's just make sure. So if we go 3 to the 5th, that's 243. So we would get 1 over 243. I don't want a decimal on that. I want a fraction, an exact answer on that. So that would mean on this problem that what we really have is we have a point on the graph is, if x is -1, the y value is 1 over 243. So we're doing arithmetic, right? Okay, we've been evaluating functions throughout the semester. We're just looking at a new kind of function here. Okay, next problem on the next page. Still exponential, so plug the number in. So when we do f of -2, we're going to have 2.3 times 0.5 to the -2, like that. Okay? Now, if you start getting into decimals and stuff, I'm totally okay with you doing this on your calculator. Let's go ahead and at least do this. We have 2.5, and then you can write this next term as times 1 over 0.5 to the positive second, like that. And that's really kind of what makes this decay, is it's going to make that number smaller and smaller. Let's just do this on the calculator. And So if you got decimals and stuff, I'm okay with you doing that. You can even type in the original. So you could do 2.3. I must have done something wrong. I think I needed 2.3 in there. Somehow my 2.3 changed into a 2.5. Is that why you two have your hands up? Okay, thank you. All right. Okay, so let's correct this then. Okay, so that goes like that. Now I'm just going to put this in your calculator. And you can go back to the beginning. It's just 2.3 parentheses 0.5 raised to the -2 power. Just put it in like that, and then we'll just take the decimal answer on this, okay? So in that case, that's 9.2. And that's okay. You just want to try to do some of these by hand. If they start getting decimals and stuff in them, try not to do them on your calculator. You don't want to get totally reliant on your calculator. Okay, next problem, f of 0. Again, we plug in, so we'll have 2 times 4 raised to the 0 minus 3. So that's 2 times 4 to the -3. This would be an example. There's no decimals. I would prefer that you do this on without your calculator. Okay, so what am I going to do with 4 to the -3? Got a negative exponent. What do I typically do? I take it to the bottom, right, to make that positive exponent, right? Okay. Now, if you need to take your calculator and work out 4 to the 3rd, you can. I know that that's 64. Okay, so we've got that. And now what you can do is you've got to reduce this fraction. I mean, you multiply fractions straight across, or you can reduce. So to me, it's always easier to reduce before you multiply. So 2 divided by 2 is 1. 64 divided by 2 is 32. So what you end up getting is 1 over 32 when you multiply that out. So I would like you to be able to do that without getting a decimal. Okay, I'd like you to be able to do the arithmetic with negative exponents. If you're going to take calculus, I know a lot of you are going to do that. Boy, you got to know what negative exponents are for sure and how to deal with them. Okay, all right, let's try to work these next 4 problems out and let's see how we do. Try to do as many as you can without a calculator. I'm okay on C if you use a calculator, just because it's got decimals in it. Although you could do C without a calculator too. I think all of these problems could be done pretty easily without a calculator. Okay. Okay, let me put up the answers here and then we'll kind of see if we have. There's a few things that I saw on maybe that second one. Okay, so I got 192, 2/3, 0.5, and 5 over 4. And again, the two that were probably the hardest to do are probably B and D, just because they have negative exponents. So this B, you ended up with 2 times 3 to the -1, and then you got to change that 3 to the -1 to 1 over 3. So 2 times a third is, remember, you always multiply fractions straight across. So 2 over 1 times 1/3 is going to be 2/3. So that's how that goes. The part C, there were 2 or 3 people who got 0.4. I'm not real sure in my mind how that happened, but you know that 0.8 to the 0 is 1, right? And then 1 times 0.5 is 0.5. So that one's easy to do. Okay, this one you get 5 times 2 to the -2. So notice I changed the 2 to the -2 to 1 over 2 to the 2nd. So it really becomes 5 over 1 times 1/4. So that's 5/4, like that. Okay? All right, does everybody understand? Does anybody need me to clarify anything? Or are we okay? Okay, all right, doing arithmetic. We're solid, it looks like. Okay, now, next thing that I want to look at the bottom of the page here is how these exponential functions work. On this one, I've given you 2 different exponential functions. And let me slide that up just a little bit there. Okay, so we're going to be comparing 2 different exponential functions. Okay, so the first thing I want to ask is, based on these numbers that are in the parentheses, are these decay or growth functions? What do you think? Growth. How do we know they're growth? They're bigger than 1, right? Okay, so both of these functions are exponential growth functions. I can't spell and talk sometimes. Okay, exponential growth function. The reason is 1.012 is greater than 1 and 1.020 is greater than 1. So we know that, okay? Now, the question is, which one do you think will grow the fastest? So what we have is we have 1.012, and then we have 1.020. Any thoughts on which one you think will grow the fastest? Which one? How come? Because it's bigger, exactly. Okay, so the faster rate is going to be this one, the 1.020. And the reason is because 1.020 is bigger than 1.012. Okay, just look at how the decimals line up. It's really 20 is bigger than 12. So you would find if you graphed those, the second exponential function would get faster, bigger. I said that backwards. It would get bigger at a faster rate, okay? All right, now an initial value, what an initial value on the next one means, it just means the initial value is when t is equal to 0. Okay, so I'll explain what we mean. You can look and tell what the initial value is in your head, and I'll show you that in a minute. So we're going to do a of 0 on the first function. That's going to be 100 times 1.012 to the 0 power. Okay, what is the answer to that in your head? 100, right? Because anything to the 0 is 1, so that's 100. So the initial value of that would be 100, okay? All right, in your head, do you know what the initial value of the second function might be? You do the same thing I just did. 95, right. See, you don't have to show the work on here because what's going to happen on an exponential function, that first number you see is going to be your initial value, okay? So what we get on this, same idea, you would get an initial value of 95 on that. So which one has the greater initial value? Well, the 100 is the bigger one, okay, like that. And again, all you got to do on initial value is just look at the number in front. That's what that says. That just means if t is 0, that's what the value of the function is, okay? Now what we're going to do is look at which one is greater after 20 years. And you don't really know that unless you do this. And we'll do this on the calculator. So we're going to do a of 20 for the first function. So we'll do 100 times 1.012 to the 20th power. Then we'll compare that to the other function I gave you, which is 95 1.020 to the 20th power. Now, before I do this on the calculator, which one do you think is going to be bigger? You mean the second one? Okay, why is the second one is correct? What do you think? How come? What makes it bigger? That thing right there. That thing right there makes it bigger. So you could actually do this in your head. You could just say, okay, the second function on that, you don't have to do that, but I'm going to go ahead and just type these in my calculator real quick and just show you on that. But once you're trying to use this information to help you learn about characteristics of these types of functions. Okay, so if I do that first one, I put that in my calculator, I get that. I do the second one. Actually, you know, the 95, I wasn't paying attention to the 95, so that we might not be able to do this in our head after all. So I need to go ahead and just crunch this out. If the initial values were the same, then the second one would be bigger, but I don't know. There's no way to tell on this one unless you can't crunch it out. Okay, so it's the second one was bigger, okay? But that's how it turns out. So this one would be about 126.9. The second one's about 141.2 if you round that to one decimal, okay? So that's how that goes, okay? All right, questions about what I just did? Okay, all right. Okay, so I want to go ahead and do this and kind of let you work through a problem like this. I want to kind of get through this part of here. Okay, so on the next page, we're going to do, given an equation of an exponential function that has the form y equals a times b the x, with these 2 points. So we're going to try to figure out what these are then. So here's what you have to do first. Step 1 is you want to use the point 0.04. Okay, you want to start with that point. So write down the function y equals a times b to the x power. Okay, like this. Okay, so what we're going to do is x is 0, so you're going to replace that x with 0. Y is 4, so you're going to replace that with 4. And if you solve this equation, we'll have what a is. Okay, so this is going to be the equation 4 equals a times b to the 0. Okay, what's b to the 0? 1. So we get 4 equals a times 1. So in other words, we get a equals 4. Now what we're trying to do in this problem is we're trying to figure out both a and b. So we got a. You want to plug that first point in to find a. The reason is because the x value is 0. That just gives you the initial value. And what that really means is that 4 will be the initial value of that exponential function. Okay, second thing you want to do is write this down. Now what we have is y equals 4 times b to the x. And you can do this in your head. If x is 0, that 4 is the initial value. So it goes there. Now we're going to plug the second point in. So we have y is 6, so that goes in there. X is 1, so that goes in there. Okay, so what we're going to get then is we're going to get 6 equals 4 times b to the first. Okay, what's anything to the first power? Itself, not 1. B to the first is what? B, right? Anything to the first is itself. So that is 6 equals 4b. Now, how do you solve that equation? Divide by 4, good. Okay, and then we'll reduce the fraction, so you can do that. So that'll get b equals 6/4, which reduced down to 3/2. Okay, then what we're ready to do is just write our answer to our problem. So the answer to the problem will go like this then. We're going to have y equals a is 4, and then b is 3/2 to the x power like that. Okay, so that's how you put that thing together. You got to use those 2 points I give you to give that answer. Okay, you guys understand what I did? Okay, let me ask a simple question on this one. Do you think this is an exponential growth or decay function? Growth, because 3/2 is bigger than 1. So when we graph this, it's going to do this. Okay, get your calculator out and let's graph it. And you'll be able to do a graph and you'll be able to tell that you're right on this problem. Okay, so put in the answer, put in 4 times, parentheses, 3/2 raised to the x power like that. And just do a standard window. You can go zoom 6, standard window like that. You can see it's a growth function based on the way that's doing that on the calculator. Okay, now all I want you to really do on this is plot a few points. So you can go to your table of values to get a few points. So if you go second graph, just find some good points. There's 0.4. That was a point we were given. So I would just use that point definitely right there and label that. That was one of the points they gave us. The other point on here that I gave you in this problem was 1/6. So it's there also. So I would just plot that point. And then the rest of it, just kind of sketch it. We know we're right because those 2 points I gave you were on there. So just kind of sketch it from here, and that's good enough. It'll approach the x-axis, but it won't cross the x-axis. So that's what that looks like. So you can tell you're right 100% on this problem. Okay? All right, why don't you all try the problem below, and we'll do the same thing and see if you can get that. You work it out the same way. Yeah. Sure, that ought to be step 1. And what that'll do is that'll give you the initial value. Because you can't, that second point won't do you any good if you use it first. You won't be able to find either A or B. So good question. You are correct. Okay, now the one thing that you always want to make sure you do on this is use the point that has an x value of 0 first, because that allows you to find a. And what will happen is whatever that value of a is, I mean, if x is 0, that just means that y value is going to be your initial value automatically anyway. So same thing on this second one. That's what the initial value is. You don't even have to necessarily do that first step. And you don't have to, okay? But you do have to do the work on the second step. Okay, everybody got that okay? All right, good. Let's take a 10-minute break, come back at 1:05, and then we're going to go over compound interest, and then we'll start talking about test. You all done?
Yes. Sorry, guys.
Did you see on the board there were 3 mistakes?
Oh, I did not.
So you don't have to do number 3.
Okay.
Number 4, I never even gave you that 6 was a 0.
Okay.
And number 5, I didn't give you 3/4 was a 0. So there's no way those problems could have been worked out.
Okay.
I mean, 4 and 5 could have been worked out if you look at a calculator. Did you get that figured out on that then?
I had it figured out.
You had it figured out already? Okay. All right.
Except for 3. I was so lost.
Okay. Number 3, I gave the wrong zeros. That's what I did. Okay.
That makes more sense to me. Those are the ones that were like tripping up a little bit.
That's the typos right. So, all right. Are you done? Did you get those figured out?
Well, I didn't get those. So should I like keep those?
Well, 3 and 4. I mean, you can turn this in Thursday. I told everybody because of those 3 mistakes, you can do that Thursday, or you may be able to finish it up, before. I'll be in my office till 4 o'clock. So.
Okay. Well, I'll be right.
So you can bring it by too if you want to.
Okay.
Good.
I'll do that. And I tried to I was running late today because there was like 3 accidents on the highway.
Really?
Yeah, and there was like one was really bad where like it went all the way down to like 1 lane. So I just want to let you know.
That's okay. Well, thanks for telling me. I think there was the day it snowed, there was a 100-car pileup on 6th Avenue. So yeah, people don't know how to drive in snow and ice very good. Okay, just sign by attendance. You need to sign?
Yeah.
Okay. An application of an exponential function. Okay, so we're going to look at the compound interest formula. So just a couple of things on here. This is the compound interest formula. And this should be pretty simple for you. Students usually do quite well with this. P is what we call the principal. That's just, how much money you start with that you put in an account. R is a interest rate. And let's see, N is the number of times. that interest is figured, number of times interest is done in 1 year. Okay, then T is just the time in years. And you don't have to write all that down unless you want to, because I've already written everything down on there anyway. So when you work with compound interest, P is going to be what you start with, and then R is an interest rate, which is an annual interest rate. N means you do interest a certain number of times in a year, and then T is the number of years that you do. And then A is going to be the amount after interest is figured out. So that's what all of the numbers in here mean. Okay, so what I want to talk about on this is we have exponential growth. So compound interest tends to work like exponential growth functions. Basically, your amount of money kind of starts off kind of low at the beginning, but as you go further and further out in time, you start making a ton of money. Okay, so if you put money in a bank account and you could hold on to it for 50 years, that would be a really good thing for you, because that's when it starts getting out of control. So the first thing that you have to kind of know about compound interest is what N is and what it means. So for instance, if you're doing monthly interest, that means you're going to do 12 times a year. So you want to be sure you write all these things down. If you're doing daily interest, we just use 365. We don't worry about leap years and stuff like that. If it's quarterly, that means you do interest 4 times. There's 4 quarters in a year. If it's semi-annually, that means you do interest 2 times in a year, every 6 months. Annually just means at the end of a year you do interest. And then hourly, I have no idea. Let's figure it out. What you would do is you would go basically like this. You would have, there's 365 days in a year. And then in basically what you would have in one day, there are 24 hours. Okay, so we just need to multiply that to figure out how many times you would do interest on that. So I'll just do that. 365 times 24 would be 8,760 times. Theoretically, you could do interest every second, and you could do it at every single instant of time. We'll talk about that too. Right, so what I'm going to show you is just basically how to use the compound interest formula. We're not going to do a whole lot of stuff with this in this section other than just learn how to use it. Okay, so we're just going to write down in each scenario what we have. So we're depositing $10,000. That means that will be your principal. Okay, the rate is 5%. Now, what you always do on this is you divide that by 100, or you just move the decimal to the left too. So if you have 5, you just move that over to get 0.05. That always, if you're using the compound interest formula, you do that because a percent is out of 100. So 5 out of 100 is 0.05. You can divide it by 100 or just in your head move the decimal back to. Okay. N, what this says is monthly. So monthly means 12 times you do interest, and then the time is 5 years. All right, so what we're going to do is, to do this problem, I would start by just writing down the compound interest formula. So it's A equals P times 1 plus R over N to the NT power, okay? Now just at least this first time, just write that down. Okay, so you're going to put the 10,000 in for the principal. Okay, then you'll have 1 plus the rate. The interest rate is 0.05. The number of compounding is 12. And then your exponent is NT, so N is 12, T is 5. And what we're going to do is just do this in one step on our calculator. So with a good calculator that you use for graphing, you should easily be able to just type this in one step on your calculator. So if you've got your calculator, please do this and make sure you can do this. Okay, so just put in the 10,000, left parenthesis, 1 plus 0.05 divided by 12. and then raised to, and then you can just do 12 times 5 and do that in there too like that, okay? And I think, Carla, don't you have a TI-83? So, yeah, just be sure that you do, on yours you would go caret, parentheses, 12 times 5. That's how you would have to put it in, okay? No big deal though, okay? So there's what we get. We're talking about money, so we're just going to round this off to 2 decimals. So the 586 will go to 59. Okay, so that's how that goes in your calculator. So the 10,000 has grown to $12,833 after 5 years. Okay, so you can just write down what that answer is, and that's how you do that. So all I'm trying to do in this section is just get you comfortable with how to use the compound interest formula. So let me ask you a simple question. You can do this in your head. You started with $10,000. You ended up with $12,833.59. How much of that was interest? How much of the final amount was interest? Yeah, it'd be the 2,833 because that 10,000 grew to that amount. So that's a lot of interest, okay? That's the way compound interest works. If you change this problem to t equals 50 years, it would be a lot more because it grows and it grows at an increasing rate, okay? All right, next problem is exactly the same idea. This time, let's say that we have lots of money and we're just going to throw $100,000 into this account. Again, the 1.5, you want to move the decimal to the left to, so that'll be 0.015. Compounding annually is 1 time. That just means you do interest every year, then for 50 years, okay? So again, just plug it into the compound interest formula. You can refer to the formula that I've got right here if you want to. So we'll just put in the 100,000, and then it'll be 1 plus 0.015 over 1, and then it would be 1 times 50. So you could put this one in your calculator like this. You don't have to worry about the ones. You could just do 1.015 to the 50th power. I mean, you can put it in either way, but it doesn't matter. I just try to do stuff if I can in my head. Okay, so I'm just going to put in the 100,000 and then 1 plus 0.015, close parentheses, and then raise that to the 50th power. So let's see how much money we have. Holy cow, that's a lot. Okay, you end up more than doubling your money. So 210,520, yeah, right. $210,524.24 is what you get. The reason that that was so big is because of the 50 years. That interest rate's tiny, and that's the way savings accounts are. In a bank, savings accounts don't draw more than 1 or 2% anymore. Kind of varies with the economy somewhat. So that would be what you end up with. Okay? All right, so if you got $100,000 laying around the house, put it in savings and wait 50 years, and you'll have that much money left over, okay? All right, go to the next page and try a couple of problems, and let's see if we can do these okay. I'll write down the compound interest formula so you don't have to keep looking back, in the different pages. Okay, so just make sure you got the right answers and put everything in there right. I didn't see too many issues with it, which is typical. This gets a little bit harder when we start learning about logarithms, when we get into a little bit later before the semester is over with. So the first one, I got $5,563.36. Second one, I got $199,153.13. Everybody good? Yeah, what I did was I kind of put this in. I hope you can see this okay. That's how the first one went on the calculator. And the second one was like this. And you have a TI, 84? 83. What the thing that you have to be careful about on the 83, because I know you've got an 83, you would have to kind of go like this. That exponent, you're going to put that caret key and then in parentheses 4 times 35. So if you got an 83, all of this would be the same way. You'd put 75,000, parentheses exactly the same, but you would have caret for exponent, and then you would either have to work that out, 4 times 35, or put that in parentheses. Okay, so probably what you did, if you didn't get those answers, is you probably didn't have that exponent in parentheses. Yeah. Was it 19,000?
That's what I got.
There's no way it would be 19,000. No way. No, 75. If you have $75,000, you're going to end up with more than $75,000. You got it? Okay. All right. Yeah, it'll be 199,153. Okay. You okay, Daniel, with how to put that in there? Did you? But make sure. See, on this, I would go ahead and work that out. That would be 3650. Okay. Because if you don't put, if you got a TI-83, that exponent needs to be worked out. Okay, that's what you can do, or you can put it in parentheses.
I also put another parenthesis after the 1 plus and then that 0, 8.
You don't have to.
I just did it.
You can, but it won't make any difference. The key thing on a TI-83 is make sure that exponent's worked out. So either work it out first or do this. Okay, all right. Okay, all right. One more thing on here then. And so let me show you what happens. The idea with compound interest is basically this. So for instance, this table right here is just showing you that if you started with $1 and you had 100% interest for 1 year, this is kind of what would happen, okay? And this is a good thing to show students. What'll happen is if you compound annually, the $1 becomes $2. Okay, and what you're going to see on there is the more often we compound, semi-annually, quarterly, monthly, daily. See, when we're at daily, we're at 365. Then we keep getting bigger. That's what you would expect to happen. The more often you figure interest, the bigger it gets. So this would be like interest every minute. There, I guess, there's like 525,600 minutes in a year. This would be every second. There's 31,536,000 seconds. So you get this. So if you look at this number, it's not going to get bigger forever. This is slowing down. See, as we get bigger, these decimals are changing less and less. So we got 2.71, 2.71. It's not going to go to infinity. Okay, nobody can get an infinite amount of money with interest. So it starts slowing down. So the idea is we get close to a number that we call E. So Euler, the mathematician Euler, came up with this just by playing around with compound interest, and he discovered that the more often you compound, if you take $1, it's going to get close to a mathematical constant. So Euler's number is E, and it's about 2.7182883, like that. Your calculator has E on it. Let me show you where that is. So if you look at your division symbol, right above your division symbol, there should be the letter E. So if you went second divide, the letter E will come out. Then if you press enter, that's what E is. E is like pi. It's a mathematical constant where the decimals go on forever. Okay, so that's what Euler discovered, is that's how he discovered that number. That number shows up in advanced mathematics all the time. Okay, so let's go to this. I want to just kind of finish up by showing you what we call the continuous growth and decay formula, and it has E in it. So basically what you have is A of t equals A e to the RT. And again, what this is going to be, that A is going to be an initial amount, an initial value. And then T, of course, is going to be the time in years. And then R is going to be a rate. So this works like an interest rate, but we use this for all kinds of things. Like if you learn about like radioactive decay, we can find a bone and figure out how old it is based on mathematics with this formula. We can work with exponential decay and so forth. All right. So what I want to do is work a little bit to finish this up with this formula, and this is called continuous. And what continuous means is that at every instant of time, we're doing like interest or we're doing a rate at every single instant of time, not secondly, not hourly, every single instant of time. Okay, so that's when you use this formula for continuous compound interest. Okay, all right. So let me go down the bottom here and show you what you need to do on this. So this one says that you have a rate of 5% per year. And basically it says in the year 2015, this is the population of deer, which was 24,000. We're going to write a function for continuous compound growth on this. So what you want to do to start with is just write down this formula that's at the top of the page. Just write down A of t is equal to A e to the RT like that. Okay. And what we're going to do on this is the rate is going to be equal to 0.05. You guys still got to move that decimal to the left too on that. And then what we'll say is the initial value will be 24,000. So you got to know where everything basically plugs in here. So what's going to happen is the A is going to be your 24,000. That's your initial deer population. Your rate is going to be 0.05, like that. So all we're doing on part A is we're just writing the function. So we'll get A of t is equal to 24,000 e to the 0.05 t. So that's how that gets put together. Okay, you got to know the initial value and you got to know your growth rate. Okay, so what we're going to do is figure out what the population is going to be in the year 2023. So basically 2023 minus 2015, the initial year, what is that? That's 8 years away. Okay, so that's 8 years apart. So t is going to be 8. Okay, so what we use is populations of animals and bacteria. They tend to follow exponential models. Okay, so what we would do is we're going to do A of 8. So we're just going to take our answer to part A, but we're going to replace the time with 8. And then we're going to put this in our calculator. Okay. So if you want to go ahead and take 0.05 times 8, you can do that too if you want to. So what you want to do on your calculator is when you're working with E, look at your first column and look at the ln button. That above that ln button, it'll say e to the x. So the way you want to put this in your calculator is you start by putting the 24,000 in, and then go second ln. That way e will automatically come out on your calculator. Then you can put in the 0.05 times 8 like that. That's how that would go in the calculator. So that would tell you that you get, and we're going to round this to a whole number. This is a population of deer. So we just kind of ignore the decimal. So we say 35,803 deer. We don't round it up. Okay, there's not 79% of a deer. We don't do that. We just take off the decimal. So that's how that goes. Those of you that have a 83, you would go 24,000 e raised to, and then in parentheses, you could have 0.05 times 8. And that should work fine for you. Okay? So again, that e comes from, it's above the ln symbol is how I put that in. Okay, does everybody see that ln symbol where e is? That's the way it is on 83 and 84 calculators. That's where you find that. Okay? Calculator okay? Yeah, good, okay. All right. Okay, so I'm going to do one problem and just let you do a couple to kind of wrap this up. Okay, so this one it says you're going to use the formula A equals P e to the RT. Okay, so if we're talking about money, we still use the same kind of formula, but we use P as the principal, R as the interest rate, T as the time. Okay, if you're continuously compounding, that's the formula you use. You only use compound interest formula like you did earlier in class if it says compounded annually, compounded monthly, or whatever. Continuous, you use that formula. Okay, so in this particular problem, the $5,000 is going to plug in, 5,500 is going to go there. The rate is going to be 0.025 because you moved that decimal back 2. You always do the decimal back 2. So you're going to develop the function. You will say A equals 5,500 e to the 0.025 times t. Okay, that's your function right there. Okay, so again, you're given an initial value, 5,500, and you're given an interest rate. So the question on B is how much will be in this account in 10 years. So now you're going to do 5,500 E times E to the 0.025 times 10. Okay, then you just put that in your calculator. So again, the best way to do the E is above is that first column above LN. So I'm just going to type in the 5,500. Then I'll go second ln. That way E in the exponent automatically pops up. Then I just put in 0.025 times 10. Those of you that have a TI-83, make sure that 0.025 times 10 is in one parenthesis. Okay, and that'll give you the amount. So if we're doing continuous compound interest, that's $7,062.14. It's money, so round it to 2 decimals. Okay, so what happens on continuous interest is that's the way you get the most money. Okay, that's better than monthly, annually, secondly, picosecondly. That's the best. That's the best you can possibly do. Okay, that's the idea. Okay, all right, so let's see if you can do a couple of problems. I'll walk around, and if you need help on your calculator. For question number 1, just use that first formula. They're both the same formula, by the way. So this formula was A e to the RT. And then for problem number 2, you can use A equals P e to the RT. They're the same formula. So that you can use the same formula for both. And just kind of see if you can get those put together okay. Okay, so if you need help with your calculator when I come around, just let me know. That's good. You're obviously doing that okay. All right. Yeah, you're doing fine. You getting your calculator under control?
Yes.
There you go. Very good. Okay, and then that just take off the decimals since you're talking about how many pairs there are. Okay, looks good. All right, so I think everybody's finding the buttons on their calculator. Okay. Maybe harder to use your phone calculator, but that's fine. Okay. Yeah, that looks good. Just take off the decimal on that first one, because you're gonna, since you're doing number of pairs, use a whole number, forget the decimal. I wouldn't round up, I would just take off the decimal. Right, you guys doing all right, looks like? Okay, yeah, you're setting it up fine, just gotta use your calculator to get your answer. Okay, and you have an 83, are you figuring everything out now, do you think? Yeah, there you go, okay. All right. Now that one, is, what, 14 years? Right. So you gotta have 0.05 times 14. So it's 14 years later. That was great. 10,471. There you go. Just take off the decimal since you need a whole number on that. On the second one, you want to round it to 2 decimals since it's money. Put that one in 2 decimals on that second one. Okay, nothing to it. If you know how to use your calculator and understand how the formula works. Okay, so let's see if we got what you're supposed to get. I think we did. So the first one, let's see, it was 14 years later from 2016 to 2030. So you ended up doing 5,200 e to the 0.05 times 14. Take off the decimal on that. The second one, you did 10,000 e to the 0.0575 t, and then t is 5, so that was $13,330.91. Okay, so when you're learning this, the thing is, how do you know to use this formula? Well, you're dealing with continuous growth. It's got to have the word continuous in it. If it has the word continuous in it, then that tells you that this is the formula that you got to use. Okay? All right, very good. All right, we'll talk a little bit about the